Okay, let's start with the basics. What asterisk is asterisk data modeling? It's really like creating a blueprint for your information systems. We're talking about designing how data will be organized and stored, so we can understand it better and use it effectively. It helps us figure out exactly what data we need, how it all connects, and how it supports our business goals. There are different levels of models, from a broad overview of the key concepts to more specific details about tables and storage. Okay, so let's talk about why data modeling is such a big deal in software development. Think of it like this: it's the foundation upon which your entire application is built. It's not just sketching out some boxes and arrows. It's really about figuring out exactly what information your program needs to work, how those pieces connect, and how that data will be used. If you don't have a solid plan for this, meaning a good data model, you can end up with messy data, performance problems, and ultimately, software that doesn't quite meet expectations. It prevents things like inaccurate reports or slower applications, so it's absolutely critical. Okay, let's talk about the different types of data models you'll often hear about in interviews, and it's important to understand them. First up is the conceptual model. This is your big picture view. It focuses on what data asterisk needs asterisk to be captured. Think of it like a blueprint for the information, using plain language terms. Then we move into the logical model, which starts defining how the data will actually be structured, tables and their relationships. Finally, you'll encounter physical models, which are specific to your chosen database system, detailing things like table names and data types. And don't forget dimensional modeling, particularly useful for data warehouses. It involves creating star or snowflake schemas for efficient reporting. Okay, so when we're talking about data modeling, it's really important to understand these three levels. The conceptual model is like a big picture overview. It tells us asterisk what asterisk information we need to capture and how those pieces relate to each other from a business perspective. Then we move down to the logical model, which adds more detail about asterisk how asterisk that data is structured, defining things like field names and types. Finally, we get to the physical model, which is all about translating that design into a specific database system, outlining exactly how it will be stored. Okay, let's start with the fundamental concept, the entity. Simply put, an entity is anything real we want to keep track of, like a customer, a product, or an order. It's basically a noun that represents something tangible or conceptual. Each entity has attributes, details that describe it, such as a customer's name and address. And crucially, each entity needs to be uniquely identifiable so we can distinguish one from another. Okay, so let's start with a fundamental concept, attributes. An attribute is basically just a piece of information you collect about something in your data model. It's like a specific characteristic or property that tells you more about an entity, which we can think of as a thing in our system, like a customer. For example, if we're modeling customers, we might have attributes like their ID, name, address, email, and phone number. Each attribute describes a different detail about the customer, and they are how we capture all those important details to make our data really useful. Okay, let's talk about relationships in data modeling. Basically, they show how different pieces of information in your database are connected. Imagine you have a customer table and an orders table. Customers place orders, right? That's a one-to-many relationship. One customer can have many orders. Then you might have a student table and a course table. Students take courses and courses have students. That's a many-to-many relationship. And finally, one person usually has just one passport, a one-to-one connection. Data modeling tools use lines to visually represent these connections, so understanding them is key. Okay, let's talk about how entities relate to each other in a database. We're going to focus on two key ideas, cardinality and optionality. Cardinality basically tells us asterisk how many asterisk of one thing can be connected to another, like one-to-one, meaning just one customer has just one account number, or many-to-many, where a student can take multiple courses. Now, optionality is about whether that connection asterisk needs asterisk to exist. Is it required, or could something be missing? So, if an order must always have a customer associated with it, that's mandatory. But if a product might not always have an image, then that's optional, and we often represent it using null values in the database. Okay, let's talk about normalization. It's a really important concept in data modeling. Basically, it's like organizing your database to make things neat and tidy, reducing duplication and ensuring everything is consistent. We do this because having redundant information wastes space and can lead to errors when updating data. Normalization comes in different forms, with 1NF being the simplest, making sure each column has only one value. Then you move up to 2NF by ensuring that all non-key attributes depend directly on the primary key. Finally, you get to 3NF, which takes care of any indirect dependencies. Think of it as a step-by-step process for creating a well-structured and reliable database. Let's talk about normal forms. They're a really important part of designing good databases. Essentially, they're rules we follow to make sure our data is consistent and doesn't have any problems. We start with 1NF, which basically means each column can only hold one value. Then we move on to 2NF, ensuring that all information in a column depends entirely on the entire primary key. 3NF builds on that by getting rid of transitive dependencies, avoiding situations where a column relies on another column that itself relies on the key. And finally there's BCNF, which is even stricter than 3NF. Why do we bother with all this? Well, normal forms help us avoid these pesky data anomalies, things like inconsistencies when inserting, updating, or deleting information, leading to a much more reliable and manageable database. Okay, let's talk about normalization. It's a technique where we intentionally duplicate some data in our database to make reading information faster. Imagine you have several tables that need to be joined together every time you want to get a specific piece of information. That can slow things down considerably. Denormalization is like bringing some of those pieces into one table so the queries become quicker. We typically use this approach when we're doing a lot of reading and not as much writing, especially when generating reports or analytics. Okay, let's talk about primary and foreign keys. A primary key is like a unique ID card for each record in a table. It ensures every row is distinct. It also can't be blank. Now, a foreign key is how we link tables together. Think of it as a reference to another table's ID column. It maintains consistency between related data. It's really about making sure your relationships are solid within your database design. Let's dive into a common interview question about data modeling: surrogate keys. Basically, these are unique ID we assign to each record in our database. They don't have any inherent meaning themselves. The main reason for using them is to avoid problems that can arise from relying on natural keys like email addresses or other system-provided identifiers. If those natural keys change, updating all related records becomes a massive task. Surrogate keys offer stability and performance, ensuring data integrity without the risk of external systems causing issues. Okay, let's talk about composite keys. Essentially, a composite key is like having two or more columns working together to uniquely identify each row in your database table. Instead of just relying on one column like an order ID, for example, you combine several to guarantee that nothing is duplicated. It's really useful when no single column alone can be completely unique. Think about orders, where the customer asterisk and asterisk the order have to be distinct. This helps maintain data integrity and make sure every record is truly identified in a reliable way. Okay, let's dive into indexes. They're super important for efficient database performance and something you'll definitely want to understand in a data modeling interview. Imagine the index at the back of a book. It helps you quickly find what you need. In a database, an index is similar. It's a separate structure that allows the database engine to rapidly locate specific rows without having to check every single row in the table. This makes queries much faster, especially when you're filtering data with where clauses. When you model your data, think about which columns are frequently used in searches and consider creating indexes on those. But remember, don't overdo it. Too many indexes can actually slow down write operations like inserting or updating data. Okay, let's talk about ER diagrams. Basically, they're a visual map of your database like a blueprint. They show you the important things in your data, what describes them, like customer names and product prices, and how those things are connected to each other. You'll see rectangles representing entities, think customer, product, or order. Ovals linked to those rectangles are the attributes that describe each entity. And finally, diamonds show the relationships between these entities, like a customer placing an order. Diagrams help us design databases efficiently and make sure everything fits together correctly. Okay, let's talk about star schemas. They are a really important concept in data warehousing and are frequently asked about during interviews. Basically, they're designed to make querying large datasets super fast. Think of it like a star. At the center is your fact table, which holds all the core information, things like sales amounts or website visits. Then you have several dimension tables branching out from that central fact table. These dimension tables hold all the descriptive details, such as customer information, product names, dates, and locations. It's a really straightforward design, making it ideal for reporting and business intelligence. You'll often see star schemas used in retail sales, e-commerce, finance, or any situation where you need to analyze trends over time. Okay, let's talk about snowflake schemas. They're essentially an evolution of the star schema. Think of them as breaking down that single wide table into a bunch of smaller, more specialized ones. It's like a snowflake. It has lots of little branches connected together. This is especially helpful when you have really complex data where you need to drill down into very specific details within your dimensions. Because we're normalizing these dimension tables even further than in a star schema, they can be a bit more complicated to query, but they also help avoid redundancy and ensure data integrity. Okay, let's talk about two key components in data modeling: fact and dimension tables. Fact tables are where you store the actual events like sales, transactions, or website visits. They hold measurable numbers and use foreign keys to connect back to our dimension tables. Think of them as the what happened part. Dimension tables, on the other hand, provide context around those events. They describe asterisk who asterisk, asterisk what asterisk, asterisk where asterisk, asterisk when asterisk, and asterisk why asterisk, things like customer information, product details, or location specifics. They allow us to analyze our data in a much more detailed way. Basically, fact tables tell you asterisk how much asterisk happened, and dimension tables explain asterisk why asterisk it happened. Okay, let's talk about many-to-many relationships, a super common topic in data modeling interviews. The key is to realize that directly relating two entities with a foreign key isn't possible. Instead, you create an intermediate table, sometimes called a junction or bridge table. Think of it as a linking table that holds the connection between your original tables. For example, if students can take many courses and courses can have many students, we introduce a student courses table. This table will have foreign keys referencing both the students and courses tables, effectively creating the bridge needed to represent this complex relationship. Okay, let's dive into something really important: data integrity. Think of it as the quality control for our databases. We want to make sure everything is accurate and reliable. Data integrity means that the information in your database stays correct and consistent over time. It's not just about having correct data, it's about ensuring accuracy, consistency, validity, following rules, and completeness. Now, how do we enforce this within our data models? Well, things like primary and foreign keys, these act like guardrails, making sure relationships are correct. Normalization helps us avoid repeating information unnecessarily, which can cause inconsistencies. Data types, like specifying that a phone number field should only accept numbers, are also key. And finally, default values ensure that certain fields always have a meaningful value. Okay, let's talk about constraints. They are absolutely vital for building reliable databases. Essentially, constraints are rules that the database enforces to make sure your data is accurate and consistent. There are several different types. Domain constraints limit what values a column can hold, like making sure an age is always positive. Referential integrity ensures that relationships between tables stay intact, preventing issues like deleting a customer without first removing their related orders. Then we have unique constraints, which guarantee uniqueness within a column. Not null constraints force you to provide a value for every field, and check constraints apply specific conditions, such as ensuring a salary is always above a certain amount. Okay, let's talk about data redundancy. It's something you'll definitely be asked about in interviews. Basically, it happens when the same information is stored over and over again within your database. Sounds good at first, right? More places to find data. But it actually creates a bunch of problems, like higher storage costs because you're using more space, and it becomes really tricky to keep everything consistent. If you update one piece of information, you have to remember to update all the copies, which is where errors can creep in. Ultimately, redundancy leads to data integrity issues, meaning your reports aren't accurate. The good news is there are ways to tackle this. Normalization is a key technique. It's all about breaking down complex data into smaller, related tables. Using appropriate data types and constraints also helps a lot. And finally, views can be really useful for combining information from different tables without duplicating the data itself. Okay, let's talk about lookup tables. They're a super helpful tool when designing databases. Basically, it's like creating a separate table that holds unique values from another table. Instead of repeating things like customer ID or product names everywhere, we put them in this dedicated table. This avoids redundancy and keeps your data consistent. It also makes adding or changing information way easier because you only need to update one place. Think about an orders table and a customers table. You wouldn't want the customer's address repeated in every order row, right? So a customer lookup table would hold all those addresses, and the orders table would link back to it using a foreign key. Okay, let's dive into data lineage. It's essentially a record of the data's journey. Think of it as tracing back every piece of information to its origins and all the transformations it went through along the way. Let's say you're looking at a sales report. Data lineage would tell you exactly which tables were used to generate those figures, perhaps pulling in customer transactions, marketing campaign results, or even product catalogs. It's incredibly useful for troubleshooting errors, ensuring compliance with regulations, and most importantly, building trust in the data itself. It adds transparency so you can confidently use your data for informed decision making. Okay, let's talk about schema evolution. It's a really important concept in data modeling. It's all about how your database structure adapts as your business changes. Initially you have a design, but things will change. Adding new features, evolving user needs, or even just realizing a better way to store data, these things require updates. Schema evolution isn't just about adding a column, it's recognizing that you need to adjust the structure to keep up. You might add attributes, change data types, rename columns, or even split tables. It's important to manage this process carefully. Versioning your database changes is a good start, and ensuring backward compatibility, meaning older apps still work with new schemas, is crucial. Then you can think about forward compatibility too, so new apps can easily use the updated structure. Phased rollouts, where you introduce changes slowly with testing, and using automated migration tools like Liquibase or Flyway for consistent deployments, are also excellent practices. The bottom line? Planned evolution is always better than trying to fix things reactively. It's a lot cleaner and more sustainable in the long run. Okay, let's talk about polymorphic associations. It's a really useful tool in data modeling when you need to represent situations where one object can have different types of relationships with another. Imagine a customer, they don't just have asterisk orders, they might also return items or file complaint. Polymorphic associations allow us to capture all these variations within the same entity, using a shared attribute to indicate what kind of relationship is in play. It gives you a lot of flexibility and avoids needing to create separate tables for each possible type of association, which can be great when things are constantly evolving. Let's talk about self-referencing relationships. They're a really important concept in data modeling, especially when you're dealing with hierarchical data like organizational charts or supply chains. Basically, it means an entity can relate back to itself. Think of a company table. It might have a field that points to the company it belongs to, its parent. It's crucial to design these relationships carefully, making sure you don't end up with circular references that could cause problems. Okay, so let's talk about how we model our data. When it comes to databases, you'll often see two main approaches, relational and NoSQL. Relational databases, think like a spreadsheet with lots of tables linked together, have a very strict structure. They rely heavily on relationships between those tables, which is great for ensuring data accuracy. But they can be challenging to scale as your needs grow. Then there's NoSQL. This is where things get more flexible. Instead of rigid tables, you might store data in documents or key-value pairs. It's built to handle massive amounts of information and easily scales up, perfect for modern applications. Ultimately, the best choice depends on what you're building. Okay, let's talk about how to handle hierarchical data in a relational database. It's a common challenge. There are a few good strategies. One approach is using separate tree tables. You'd have a table for the root nodes and then child tables linked by foreign keys. Another technique involves nested sets, where you store all the relationships within a single table, but that can get a little tricky with updates. Finally, path enumeration stores the entire path from the root to each node in one column. This works best if those paths don't change much over time. Think about which method makes sense based on your specific data and how it will be used. Okay, let's talk about modeling relationships. It's fundamental to good database design. We have three main types. One-to-one, where each record in one table connects to only one record in another, like a person and their passport. Then there's one-to-many, meaning one item can relate to several others, like a customer placing multiple orders. Finally, we get to many-to-many, which needs a little more thought. It's where multiple items connect with multiple other items, usually requiring an intermediate table or a junction table to link them together. Okay, let's talk about data dictionaries. They are really important for understanding how a database is structured. Imagine it like a detailed catalog. Every table gets its own entry, listing all the columns within it. It tells you what each column asterisk is asterisk and what kind of information it holds, like whether it's text, numbers, or dates. Crucially, it also explains what those columns actually asterisk mean asterisk. Without a data dictionary, everyone on the team could interpret the same data differently, which can lead to some serious problems down the line. So, think of it as your central source of truth for all things database. Okay, let's talk about the foundation of good data modeling, domain modeling. Basically, it's like creating a blueprint for understanding how a specific business area works. We're talking about taking something real, say how your company handles customer orders, and figuring out what the important pieces are, how they relate to each other, and what information we need to capture about them. This isn't just about designing databases, it's about truly understanding the business problem you're trying to solve with data. Interviewers really want to see if you can do this, translate those messy business needs into a clear, organized model. Okay, let's talk about how data modeling changes depending on the type of system we're building. Transactional systems like your online store or a bank are all about getting things done asterisk right now asterisk. They need to process individual transactions quickly and accurately. So, the data models tend to be very highly normalized, meaning they avoid repeating information and prioritize data integrity. They're built for small, frequent updates. Now, analytical systems, like those used for business intelligence, are focused on understanding the past to make better decisions in the future. They deal with huge amounts of historical data. Their models often denormalize, which can lead to some redundancy, but allows for much faster querying. Think pulling together sales figures over a period of time. Okay, let's talk about data warehouses. They're really different from the databases you might use every day for running your business. A data warehouse is like a giant collection of historical information pulled together from all sorts of places: sales records, customer details, marketing campaigns, and more. It's built specifically to help us analyze trends and spot opportunities. The way we organize this data is important, and it's usually done using something called a dimensional model. The most common ones are star schema and snowflake schema. A star schema has one central fact table like sales figure surrounded by smaller tables that describe what the sales were about, the customers involved, the products sold, when they happened, etc. A snowflake schema is similar but takes things a little further, breaking down some of those descriptive tables into even smaller ones. Basically, data warehouses are all about looking back and understanding why things happened. Transactional databases handle the day-to-day operations. Okay, let's dive into dimensional models. These are a really common technique used when we're looking to analyze past data, think sales records or customer activity. The main idea is that instead of trying to represent everything in one huge, complicated table, we break it down into smaller, more manageable pieces. We focus on facts like actual sales numbers and then build dimensions around those facts, which give us the context, such as who made the sale, what product was sold, and when it happened. It's a structured way to organize data that makes reporting and analysis much easier and quicker. Okay, let's talk about slowly changing dimensions. Basically, these are dimensions, things like customers or products that change over time. Imagine a customer who used to buy blue shirts but now prefers red. Traditional data modeling can get tricky when you want to keep track of how those changes happened and what the values were at different points in time. Instead of just replacing all old information, SCD let us capture the history of these shifts, which is super important for things like reporting and trend analysis. There are different types of SCD designed for varying levels of change and historical tracking. It's about choosing the right approach based on your specific needs. Okay, so let's talk about how we handle changes to our data models. It's super important for keeping things consistent. I always start by using a version control system like Git. Think of it like tracking edits to a document but for your whole model. Then I use semantic versioning, which is a way of numbering releases that tells you exactly what's changed. Major changes mean big shifts, minor changes add features, and patches are just bug fixes. I also keep detailed records of every change in a separate history table to easily understand how things evolved. Finally, it's important to think about compatibility, ensuring new versions can work with older systems without causing issues. Okay, let's talk about how we think about database schemas. We often face a choice between two main approaches, normalization and denormalization. Normalization is all about reducing redundancy, breaking your data into smaller, more manageable tables to ensure everything stays consistent. It's great for maintaining data integrity, but can sometimes make complex queries a bit tricky. On the flip side, denormalization deliberately adds some redundancy back in to speed up reads and simplify questions. If you're building a reporting system where performance is key, it might be the better option. The trick is figuring out which balance, integrity, or speed is most important for your asterisk-specific application. Okay, let's talk about schema on write versus schema on read. Schema on write is like having a very detailed blueprint before you even start building. The database strictly enforces this structure when data is written in. It's great for consistency and validation, but it can be less flexible if your requirements change later. On the other hand, schema on read is more adaptable. You define how the data should be interpreted when you're querying it. This offers a lot of flexibility, but might mean slower performance for complex queries because the database has to figure things out on the fly. It's all about choosing the best fit for your specific needs. Okay, let's dive into eventual consistency, a really important concept when you're thinking about how data is stored and accessed in distributed systems. Basically, it means that updates to your database aren't always immediately visible everywhere. It's like updating your bank balance online. The change might not show up instantly on every screen or device. This delay is eventual consistency. This has a big impact on how we design our data models. We often need to relax some of the strict rules about immediate consistency, and we have to think carefully about conflict resolution strategies. It's all about balancing availability and scalability with the need for reliable data. Okay, let's talk about how we handle relationships when working with document databases. These systems are really flexible because they don't force you into a strict table structure like traditional relational databases. But that flexibility means you need to be strategic about how you model those connections. One common approach is embedding, which just means including the related data directly inside the main document. This works great if you frequently need both pieces of information together. Alternatively, you can use referencing, where you store an ID that points to another related document. This requires a bit more work when retrieving data, as you'll essentially be doing a join operation, but it's often better for less common relationships. Finally, many developers use a hybrid approach, embedding what they need most frequently and referencing the rest. Think about how often you actually need to access that related information. That's key to deciding which strategy is best. Okay, so when you're asked about data modeling tools, don't just rattle off names. Think about the range of options out there, from established commercial products like ERWin and SQL Developer Data Modeler to more flexible diagramming software like Lucidchart. And remember that even simple tools like Excel can be useful for visualizing your ideas. The key isn't necessarily which tool you know, but how well you can represent data concepts in a way that's understandable to stakeholders. Okay, let's talk about scalability. When you're building a database schema, it's easy to focus on the current needs, but you have to think about how that model will handle growth. There are several things you can do. First, understand the difference between normalization and denormalization. They both have advantages and disadvantages. Then consider horizontal scaling, which means spreading your data out across multiple servers. Sharding is a specific type of this, where you divide your data based on common query fields. Don't be afraid to think about partitioning data by date ranges too. And really importantly, design with the future in mind. Don't lock yourself into a rigid schema that won't adapt as new data types or relationships emerge. Finally, choosing the right data structures can make a huge difference. Okay, let's talk about some really interesting hurdles you might encounter when designing data models for systems that spread out across multiple computers. It's not just about fitting the data into tables, it's about how that data behaves across those machines. One big thing is figuring out whether you need immediate consistency, where every update shows up everywhere instantly, or if you can tolerate a little bit of delay, sacrificing perfect accuracy for higher availability. Then there's the challenge of splitting your data across different server sharding and deciding how to do that smartly so queries are fast and resilient when one part of the system goes down. And don't forget about conflicts. When multiple people or systems update the same information on separate servers, you need a plan for resolving those disagreements. Network problems and failures also throw curveballs. Your data model has to be designed to handle delays and potential outages gracefully. Finally, as your system grows and changes over time, your data model needs to be flexible enough to adapt without major rework. Let's talk about entity inheritance, a really handy tool when dealing with related entities. It's like building upon an existing foundation. You create new entities that inherit all the characteristics of their parent, but also get to add their own special features. Think of it as a family tree. Children share traits from their parents while also developing their own unique qualities. This approach helps us avoid repeating data, keeps our models tidy and easier to update, and makes things more reusable overall. Okay, let's talk about modeling time series data. It's a really common interview question. It boils down to understanding how your measurements change over time. First, you need to confirm if the data is actually a time series. It needs a consistent interval in chronological order. Then, figure out the frequency. Are we talking hourly readings or monthly sales figures? Once you have that, decompose the series into its components: trend, seasonality, cyclicity, and noise. There are various modeling approaches like ARMA models, exponential smoothing techniques, or even state space models depending on the data's characteristics. And crucially, don't forget feature engineering. Creating new variables from your time series can dramatically improve model performance. Okay, let's talk about a really important decision when building your NoSQL data models. Should you embed related data within a document, or should you reference it to another document? Embedding is great when you need immediate consistency and frequently access the subdata together. Think of it like keeping all the ingredients for a cake recipe in one box. Everything's right there. However, if your relationship is more complex, or if that smaller piece of data isn't always needed, referencing can be much better. It keeps things separate, lets you change them independently, and avoids unnecessary duplication. It's like having a list of ingredients and knowing where to find them. It's simpler and more flexible. Thank you for watching.